All right, welcome back to our Thermo II Series video. This is part 2 on our discussion on psychrometrics, and we are going to be talking some more about the dew point and some of the properties that that are associated with mixtures of air and water. So first we're going to start by defining the dew point, and it's best illustrated on a TS diagram as such, and I'm going to put 3 isobars on this TS diagram. You'll see why in a moment. It'll make sense then. But right now, let's say I got these 3 different isobars that are going on the TS diagram for water, and let's say the top one is at 70 degrees Fahrenheit. And let's just say that that middle one is where my moist air sample is on. So in other words, the partial pressure of water in that moist air sample is this P sub B, as we saw previously. So the dew point is simply defined as that saturation temperature at that partial pressure. So the temperature at which the moist air sample that I have finally starts to condense. So obviously it requires some heat transfer, right? I'm going to take this water sample, this sort of moist air sample, I'm going to cool it down until finally it starts to condense. So I'm writing down that middle isobar there from the right to the left until it hits the dome. So so the partial pressure of the vapor, P sub V, by Dalton's law, is equal to the mole fraction of water in the mixture times the total pressure of the mixture that I have. Just as a refresher here, my isobars are getting higher and higher pressure as I move to the right, as shown right here. So the middle one is the middle pressure, the one above it is a slightly higher pressure. Okay, so using this definition of dew point, we're going to put all these properties and new concept that we've learned about psychrometrics into an example. So in this example, we're going to consider a 1 pound of moist air. So it's a sample of 1 pound. Imagine that you go outside and you capture 1 pound of air, outside air, at 70 degrees F, when the pressure is 14.7 psi and the relative humidity is 70%. And then you take this sample, this 1 pound sample that you grab from outside, and you start cooling it down at 40 degrees F, and you do so at constant pressure. So you can imagine that you have like some sort of a piston cylinder arrangement here that keeps that constant. And some of the questions that we're interested in figuring out on this moist air mixture is what is the initial specific humidity. Remember, we defined that last class in part 1, also called the humidity ratio. The final specific humidity, the dew point, and how much water condenses, if any, in the process of cooling the sample from 70 degrees F to 40 degrees F. Okay, so recall that this specific humidity is denoted by omega, so I'm putting that down here. And here's the 70 degrees F point that I've talked about before. That's our top isobar, and the P sub V right there is supposed to be aligned with that 70 degrees F, right? And 60 degrees, we're going to see why that's important in a moment, and the 40 degrees F is there as our final point. We don't know exactly where we're going to end on that curve just yet. So we've got our given, our find, our sketch, our model / assumptions. We're going to assume the typical thing with psychrometrics, that we can model the air and the vapor as a mixture of perfect gases, and that the only thermal energy that we have in a mixture is the only stored energy that we have in a mixture is the thermal energy. So we're neglecting kinetic and potential energy. All right, and we're going to jump around a little bit in the solution process here. We're going to do part C first, the dew point, because it's easier to look up. So as defined above, the dew point is that saturation temperature at that constant vapor pressure. So we know the vapor pressure because we know the relative humidity in the mixture in the first place. Or I should say we can figure out the vapor pressure. So that's what we're going to do next. We're going to figure out that vapor pressure first for that water mixture. So saying that the relative humidity is 70%, as we saw last class, means that the ratio of partial pressure of the vapor to the saturation pressure at that same temperature is 70%. So we can go in the table in the back of our book, or saturated vapor pressure, or use ease to figure out what the saturation pressure is at 70 degrees F, and it's about 0.3632 psia. And so therefore, that gives us readily the vapor pressure, the partial pressure of the water in the mixture as 0.7 times that, or 0.254 psia. So yeah, so now we know the partial pressure of the water, and we also know the saturation pressure of the water. So next we need to know at that particular vapor pressure what the saturation temperature that's associated with that. So again, we can look at our saturation tables, table 8-2E in the book, or use ease to figure out what that saturation temperature, and we find from the book that it's 60 degrees F. And so that would be our dew point. We're writing that isobar down by extracting heat from the sample until it finally condenses, and then it's going to condense at 60 degrees F when the relative humidity is 70%, is what we figured out. Here's another way to do this. We're going to repeat that last exercise here using ease. So our mixture temperature is 70 F, and our partial pressure for the vapor is 0.254, we found. So what is the saturation temperature of that mixture, meaning the dew point, and what is the partial pressure of the saturation pressure of the water at that partial pressure for the vapor. So ease allows us to figure that pretty straightforward. So the saturation pressure at the temperature of the mixture is going to give us that value that we just calculated, and the saturation temperature should be around 60. Let's see what we've got here. Let's adjust the units and hit the calculator button. Boom. So the saturation pressure is indeed 0.3633. Using ease, we found 0.3632 from the book, close enough. Saturation temperature, which is the dew point, is found through ease at empirically as 59.74, approximately 60 degrees F. So you see two methods here for figuring out both the saturation temperature and the saturation pressure that we need for these calculations, right? So so now we're back to figuring out the initial specific humidity, which, as you'll recall, is defined as the mass of the vapor over the mass of dry air. So if we start off with 1 pound of total mixture, that means that we're going to have a sum of MV plus MA that gives us 1 pound, and then we can massage each individual component here to express it in terms of partial pressures using the ideal gas law, and so that's what equation 2 is giving us here. The mass of vapor is going to be a function of the molecular mass of the vapor of water, its temperature, and its partial pressure. Same with the air, and since the volume, the temperature, and the universal constant are the same, we're going to be able to readily figure out what the humidity ratio is simply by dividing equation 2 and equation 3 together, and end up with a pretty straightforward expression for the humidity ratio in terms of partial pressure and molecular mass of the constituents. So we've already figured out what P sub V and what P sub V is, and since we know the total pressure is 14.7, that tells us that the partial pressure of air is simply going to be 14.7 minus that 0.254 psia. Molecular mass of vapor of water is 18, that of air is 29 kilograms per kg per kmol, of course. So now putting all this together gives us a humidity ratio of, or specific humidity of 0.01091. So that's in pound mass of water per pound mass of dry air. We're going to box our answer to part A right here to make that clear. Okay, and that comes about by equation 4 that we have on the right. So this is a kind of a nice, clean way of expressing your answers. By the way, I really like this. I'm just letting you know here. It makes following the work that you're doing, even when you're crunched on time, rather quickly, rather easy to follow. Okay, going back to equation 1, let's figure out how much air we have in there. And how much vapor we have in there too. So we have, out of the 1 pound, we have 0.0108 pound mass of vapor and 0.9892 pound mass of dry air. Remember, we can't just get it straight out of the omega value of specific humidity because it's normalized by pounds of dry air, and of course we have a different mass. Here I'm introducing a new system of units, grains, which is typically used in the study of moist air because the numbers are not so tiny when we're looking at the actual mass of vapor in the mixture. There's 7,000 grains per pound mass. Continuing on, so that we can see what's going on at 40 degrees F, where we're going to end up at, we find that the saturation pressure at 40 F, again I could have done this in ease, but I took it from the book. The saturation pressure at 40 F is 0.1217 psia, and since this is less than 0.254 psia, which is what the original vapor pressure of the sample is, that means that water is going to have to condense, right? So the saturation pressure is less than the local one, so we're going to be condensing some water. Another good clue for this is that the final temperature, 40 F, was less than our dew point. So we're going to have to pass through the dew point in order to get there, right? So after cooling at 40 degrees F, since the pressure is constant when we're doing this process, then the air pressure must have changed. The partial pressure of air must have changed. Again, imagine a cylinder with a weighted piston, that maintains a constant pressure inside. This is sort of what we're doing here in this analysis. The final specific humidity is going to be, per our previous equation, the ratio of the vapor pressure of water divided by the partial pressure of dry air at the end of the process, and that's what we just calculated there. Oops, that's right, we have a factor here of the molecular mass that we have to include in there. Remember, that's part of that equation 4 up there, so we better express this correctly. So we're missing a ratio of molecular mass on the right there, so let's add that up. So that's going to be 18/29, and therefore the final humidity ratio, or specific humidity, is going to be 0.00518, tiny number, so the grains is going to be a more practical system of units for us to use. And incidentally, that's still a system of units that's used in the aerospace industry. When I worked at Allied Signal or Honeywell, this is how we expressed humidity in air conditioning systems for airplanes, and grains of water per pound mass of dry air, exactly like this. So numbers around 30 to 50 are common. So there we go. The final humidity ratio is going to be 36 grains per pound mass of dry air, or 0.0518 pound mass of vapor per pound mass of dry air. Okay. What else do we have here? Oh yeah, we're trying to figure out how much water gets condensed in this. This is our last part D. So in order to do this, we're going to need to figure out the mass of water vapor that's left in the end after we've done some condensation. Since we now know the humidity ratio at the end, that should be possible, right? So that'll be our first step. So back to our endpoint humidity ratio. That means that the mass of vapor that we have is going to be the humidity ratio times the mass of air that we have. And so we have a final mass of vapor of 0.05124 pound mass. And since we know that we started with 0.0108 0.108 pound mass. We're going to be able to subtract that to get the amount of water that had to have condensed to give us this smaller quantity at the end, right? Final, the initial mass, sorry. So the water that condensed is going to be that minus the final vapor mass. So 0.0108 pound mass minus 0.005124 pound mass, giving us 0.005676 pound mass that had to have condensed, or about 40 grains. And voila, 40 grains or 0.005676 pound mass of water was squeezed out of this mixture as we cooled it down. Thank you, and see you next time.